Hello, my name is Eloise. In the last lesson, we investigated some flat shapes and some right rectangular prisms. We saw what happened to the surface area of a shape or a right prism when we increased its dimensions. Now we will look at another right prism, the cylinder. By the end of this lesson, learners should be able to estimate and calculate how a decrease in the radius and height of a cylinder changes the total surface area of the cylinder. Here is a right cylindrical prism. If I want to know what its total surface area is, I need to work out the area of this circle and the area of this part around the cylinder. How do we find the area of this part? Do you remember how we can use the net of the cylinder to help us with this? If you unfold a cylinder, this part makes a rectangle. This length of the rectangle is the height h of the cylinder, and this breadth of the rectangle is the same as the circumference of the circle. The formula for circumference is 2 pi r. So the area of the rectangle is 2 pi r times h. What about the area of each of the circles? By now you should know this is pi times r squared. There are two of them, so we have 2 pi r squared. The total surface area of this cylinder is 2 pi r h plus 2 all multiplied by pi r squared. The diameter of this tin cylinder is 7,4 centimeters. That means the radius must be half of that, 3,7 centimeters. The height is 23 centimeters. Putting that into the equation, I get 2 times 3,14 times 23 times 3,7 plus 2 times 3,14 times 3,7 squared. I get 620,4 squared centimeters for my answer. Now here's the challenge. How will this surface area change if we halve the height of the cylinder? Can you see the two circles have not changed in area? Only the height has changed, and this changes the area of the rectangular part of the net. We will get half of this number. Added to this number, the answer is about 353 squared centimeters. You can check my workings on a calculator. So this cylinder has a surface area of about 620 square centimeters. This cylinder with half the height of the other one has a surface area of 353 square centimeters. That's more than half of 620. Although the height is halved, that doesn't make the surface area half of the bigger one. Now let's have a look at what happens if we halve the radius of the cylinder. Our new cylinder will have a radius of half of 3,7 centimeters. That's 1,85 centimeters. Let's stop here and think about this. What do you expect to find? Make a conjecture about the area of the smaller circle. A conjecture is an informed opinion that you wish to show to be true. How much smaller is it than the original circle? The area of the new circle is pi times r squared, which is 3,14 times 1,85 times 1,85. That comes to 10,75 square centimeters. The big circle was 3,14 times 3,7 times 3,7. That's 43 square centimeters. The area of the small circle is 4 times smaller than the area of the circles on the bigger cylinder. Did you notice that we squared the radius to find the area of a circle? So squaring a half times the radius will make a quarter times the radius squared. So the whole surface area of this container will be the area of these two circles. That's 2 times 10,75. And now, what about the surface area around the cylinder? What do you think we will find? How much smaller do you think this surface area around the container is than the area on the original cylinder? Well, the height is the same, but look at this net of the cylinder. This length here is smaller because it is the circumference of the smaller circle. Let's work it out. So the total surface area is smaller when you halve the radius of the circle than the total surface area when you halved the height. That's fascinating, don't you think? If we have another look at the formula for the surface area, this actually makes sense. Can you see that the value of the radius will affect this term in the formula and this term? But the value of the height only affects this part of the formula. So a decrease of the radius is likely to have a greater effect on the total surface area than a similar decrease in the height. Well, we looked at a change in height and a change in radius, but now we haven't tried to investigate what happens when both height and radius are reduced. We made this cylinder that has a radius of half the radius of the original and half the height of the original. Looking at it, what would you like to predict about the surface area? Will the surface area be half of the original, a quarter of the original, or even smaller? Don't rush into answering this one. We are halving the height and halving the radius. The effect of halving the height, we have seen this before. It will halve the area of the rectangular part of the net without changing the area of each of the circles. Halving the radius will make each circle's area 4 times smaller than the original size. This makes sense because r divided by 2 and then squared gives r squared divided by 4. The smaller radius will also cause the circumference to be smaller. Remember that the circumference becomes the length of this area around the cylinder. If we look at the formula for surface area, we could improve our prediction. Have a look. The radius is halved and the height is halved. We get So using the formula, it looks like our new surface area will be a quarter of the original surface area. Let's see what we get with our calculations now. 155,1 goes exactly 4 times into 620,4. Altogether, the surface area of this new cylinder will be 4 times smaller than the surface area of the bigger one. If you compare their nets, you might believe me. Does it look as if this net could fit into this net 4 times? Halving the radius and the height of the cylinder results in a surface area that is exactly 4 times smaller than the original surface area. Here is your task for this lesson. 1. Find the total surface area of this right rectangular prism. 2. If the length of the prism is halved, find the total surface area of the new prism. 3. If the length, the breadth and the height of the prism are halved, find the total surface area of the new prism. That brings us to the end of surface area. Till next time, goodbye.